Hi everyone, so let's continue to the next topic, which is to predict the mass transfer coefficient and design of absorption tower for concentrated mixtures.
So in this part 1 of the video, at the end of this part 1, you should be able to achieve the following. So actually for this topic, we have 3 learning outcomes from this topic alone. But for this part 1, you should be able to use appropriate correlations and available data with respect to systems of interest and packing specification to predict the mass transfer coefficients, and also to estimate the percent resistance in the gas or liquid film in a given absorption or stripping process specification. So the next learning outcome, we will cover that in the part 2 of the video. So how do we determine the film coefficient values? So you need to know that the individual film mass transfer coefficients, the KYA and KXA, these values depend on the transport properties of the gas and liquid. So generally it depends on the Schmidt number, the gas and liquid mass velocities, and the size and shape of the packings. Okay, but the interaction for all these factors, the Schmidt number relating to the gas and the mass velocity of, the gas and liquid mass velocities, the size and the shape of the packing, the relationships are quite complex. So the correlation for the mass transfer coefficients are actually empirical. There is no sound scientific basis as to how we get the correlations. Thus, the reliability of the correlations is not too satisfactory. So you can expect up to 25% deviation. Okay. So how do we measure the coefficients experimentally? Is we need to arrange an experiment such that the other film resistance is negligible, or you can approximately calculate the film resistance of either the gas or liquid phase, or you can neglect make it negligible for either gas or liquid phase. So for example here, if you want to measure KXA and KYA, so let's just have a look at the measuring KXA first. So this KXA is the liquid film mass transfer coefficient. So for this, to measure KXA, you need a system to absorb very insoluble gases, highly insoluble gases in water, such as oxygen and carbon dioxide. So in this case, since the gases are very insoluble in water, you can say that the gas phase resistance is negligible. Thus, the value will give you KXA, the capital K, and also that will be equal to the small k, because the gas phase resistance is is negligible. And from this value, you can get the HL. You can refer to the relationship between KXA, HL, and the capital KXA from the previous notes. Okay, so similarly, if you want to measure KYA, so KYA is the gas phase film coefficient. So to measure this, you use a system such that now the solute is very soluble, highly soluble gas in the liquid, and thus the liquid phase resistance is negligible. So an example of such system is the NH3 air water, so ammonia. Ammonia is very soluble in the liquid, so the liquid phase resistance is negligible. The liquid phase resistance is known to be about 10%. So if you know that the liquid phase resistance is about 10%, so whatever value you get for the gas phase film coefficient, you can subtract the 10% known resistance to obtain the KYA, and then you can get the HG. Okay. Okay, so how do the correlations look like? So the correlations from experimental coefficients, it can be expressed in terms of HL or HG, or in terms of KXA and KYA. So you can refer to the relationship between HL, HG, KXA, KYA in the previous notes, okay? Actually for first generation of packings, i.e. the old packings, for example, Rashik rings and Bell saddles, extensive correlations are available. But all of these correlations are empirical, so there is no one reference that is the most correct for you to use to get the correlation. So in this case, we got it from the textbook uses this data from this publication, from this book, Trable, mass transfer operation, and this must be coming from literature, from experiments that the researchers has done. So we take this value as an example. Okay, so for example here, this is for Rashid ring and Boyle saddle. They have the values of alpha, beta, gamma, and the range of validity for this alpha, beta, gamma of the GY and GX. So what are the GY and GX? These are the value of mass flow rate of the liquid and of the gas. So GY is the kilogram of total gas per second per unit area per meter square, and GX is the mass flow rate in terms of a kilogram of liquid per second per meter square per unit area. And also NSC, the Schmidt number, you know, it's mu over rho times D. So if we're talking about the gas phase, then the Hg, so this is the correlation, empirical correlation, alpha times Gy to the power of beta times Gx to the power of gamma times with the Schmidt number to the power of 0.5, and the Schmidt number you can calculate from the viscosity of the gas mixture, density of the gas mixture, and the diffusivity of solute A in the gas. Okay, so let's say if you have an existing data for solute A in a gas on a specific packing of absorption, let's say Rashid rings, a 9.5 millimeter size, so you can use alpha, beta, gamma here, the values here, within the range of validity of Gx and Gy, and you can compare that to get a correction to get the Hg for solute E in the same system, in the same gas, and using the same packing. So let's say if you already calculated the Hg for solute A in the gas, then you can get the Hg for solute E in the same gas, in the same packing, from this correction factor. You just need the NSC of the solute E. So solute E NSC, you can calculate it using this. So you need to get the viscosity, density, and the diffusivity in this case of solute E in the gas. Okay. So in the previous slide, it was given the correlation for film coefficient of the gas phase, liquid coefficient, film coefficient. So this here is the film coefficient for the liquid film. So you can see that this is HL and then this is GX. GX always refer to the liquid phase. So the range of validity for the GX is this, and you have to always check the unit. So 0.542 of what? Kilogram per second per meter squared until 20.34. So beyond that range, you cannot use this value of theta and eta. You need to find other literature which can work for your range of Gx if it's not within this value. So as usual, also NSC for liquid phase, now the viscosity is for liquid viscosity and the density is for liquid density, and the D is the diffusivity of solute A now in the liquid phase. Okay, so just always be careful with the units, especially in the dimensionless numbers here. So those in the previous slides are the correlation for film coefficients for old packings, the established packings such as Rashid rings and Boyle saddles. But for newer packings, comprehensive data are not generally available, but however, the newer packings are the ones that are more commonly used nowadays. So an alternative method to compare the performance of the different types and sizes of the newer packings, you need to have some correction factor lah. Okay, for example, you can conduct an experiment using the system of CO2, air, and NaOH. So NaOH here is the solvent, CO2 is the solute, and air is the carrier gas. So you can say that, okay, let's give an air containing 1 mole of CO2 at 24 degrees Celsius at, in the Western countries room temperature. This is the not common room temperature. Is absorbed in a packed tower using 1 NOLA, i.e. the 4 weight% of NaOH solution. Then you can measure the overall kGa. So in this system, the liquid film is controlling, but the gas film resistance is not negligible. So you need to measure the concentration gradient for CO2 in the water film, actually in the liquid film, and also in the gas film. Okay, so but in this case, the value of kGa is much larger than for absorption of CO2 in water, And because of this, these experimental values are not used to predict the absorption for other systems in the towers, because this is actually a reactive absorption. So all in all, it's okay if you don't understand this part of the slides, because you just need to know that for newer packings, you need to have some correction factor, and you need to have some system of solute, carrier gas, and solvent to get some corrections to compare with the older packings correlations. That's all. Okay, don't worry. This is too specific for the application. You just need to know the general understanding only. Okay, yeah, for this slide also, you can just read. Okay, you just pause the video and read through. It's just to say that for newer packings, we have this factor, FP, the packing factor, as a correction factor based on the correlations of for older packings. That's all this slide is trying to get the point across. So you can read, and if you have questions because you're interested to know more, then you can ask question, and I will try to find the answers for you. Alright, so these are how the correlations look like for newer packings. So when we say newer packings, we still have these ratchet rings and ball saddles, but maybe for different materials. So now here is a ceramic and pawl rings, like metal interlocks, no pack, high pack, and these are for random packing, and this is for structured packing. So you should know what's the difference between random packing and structured packing. So you can have a look at the values here. So the void fraction is given in this column, and this column here gives you the surface area. The value without the bracket gives you in the unit of square feet per cubic feet, and the value in the brackets here gives you in terms of meter squared per meter cube. And the packing factor also, the ones without bracket is for per unit foot, -1, and in the bracket is for per meter. And these are the relative mass transfer coefficient FP. Okay, these are the values of FP. So some don't have the values of FP, so maybe you can just take one if there isn't any values. Okay, you can't take 0 because otherwise your correlation won't work. So these are some examples of the correlation for Hg and Hl from this table that you can use from using the values from this table. So for example, Hg, you see the values here. You need the value of Fp, the Schmidt number for the gas phase, Gx and Gy. And also for HL, you need the packing factor as well, and see the Schmidt number, and you only need the Gx and the viscosity of the liquid. So you don't need Gy in the correlation for HL. And must remember that these correlations have ranges of validity. The value in which the flow rate, it only works in certain values of flow rate. So you must always refer to the literature to check if the correlations are applicable to your system of interest. If not, then you need to find other methods, okay, other correlations. Alright, so let's go through example 1. So consider the absorption of ammonia from water in a dilute solution with air in a packed tower with 25.4 mm ratchet rings at 303 Kelvin and 101.32 kilopascal pressure. The flow rates are given. So the flow rates are Gx. So this is the liquid flow rate. The unit, look at the unit, 2.543 kilogram per second per meter squared. And the gas flow rate, Gy, equal to 0.339 kilogram per second per meter squared. So you are asked to A, predict the Hg, Hl and Kya, and B, to estimate the percent resistance in the gas field. So you're given the data here. Equilibrium relation in a dilute solution for the system ammonia, air, water at the given temperature and pressure is Y equal to 1.20x. And for air at 303 Kelvin, the mu and the rho, okay, viscosity and the density are given. Diffusivity of ammonia in the gas phase is also given. And for water, the viscosity and the density is also given at this temperature. and the diffusivity of ammonia in water at 303 K is also given. So this is because it's an exercise, it is an example, so you're given all of this data. But if you're not given all of this data, you need to find it out on your own later when you do your own design of an absorption tower, for example. Okay? Alright, so the solution, for example, 1 part A is to calculate Hg, HL, and KYA. So we start with the Hg, the gas phase first. So we take this table from the book, table 10.81, the gas film height of a transfer unit Hg in meters. So we can use the correlation here. Hg equals to this. So we need the value of alpha, beta, gamma, and NSC, the Schmidt number. So we calculate the Schmidt number for ammonia in air. The viscosity of ammonia, the gas mixture is given, the density, and also the diffusivity of ammonia in air. So you get NSC equal to 0.669, and then you use the data from the table here for 25.4 millimeter Rashid ring. 25.4 millimeter Rashid ring. So the alpha is here 0.557, and the beta 0.32, and the gamma negative 0.51. Okay, so the range of values must be GY must be between 0.271 and 0.814, and GX must be between 0.678 and 6.10. Okay, so you have your, okay, so you put all the numbers here already. So alpha is 0. You just plug in the numbers into this equation. Okay, so GY is 0.339 within the range, and GX is 2.543. Is it within the range? Yes, it's up to 6.1, so it's within the range. So then you get Hg equal to 0.200, correct to 3 significant figures, meters. And so this is your Hg. So next we want to calculate HL. So we start with the Schmidt number for ammonia in water. So the viscosity divided by density times the diffusivity. So you get 303.1 as the Schmidt number. Okay, so to calculate the HL, the correlation for HL is given there. HL equals to theta times Gx over mu L to the power of eta times NSC to the power of 0.5. So theta, you take from the table, Rashid rings 25.4 mm. So the theta is this, okay, this, and the eta is 0.22. So just plug in the numbers, and you get the HL equal to 0.2412 meter. And then to find KYA, so you need to use this relationship which we have derived in the previous lectures on absorption. So then we need to find what we need to find. Okay, for example, in this case, you know the Hg, but you don't know the KYA and S, so it will be cancelled out anyway. So you calculate this KYA equal to V over HGS. Okay, but as you can just ignore. So here you just need to be aware or be careful of the units, because our given gas and liquid flow rates in the question is in mass flow rate. Mass flow rate, kg per second per meter squared. So that's why we can just ignore the S here, because S here is the cross-sectional area. So you take the, for example, V, you take the GY. So the GY was in kilogram. So you divide by the molar mass of air, approximately 29. So that will give you the molar flow rate. Okay, that will give you in terms of kilomole per second per meter cube times mole fraction, per mole fraction. Okay, so because Hg is, the unit is meter, okay, S is, the unit is meter squared, and since your unit for mass flow rate here is kilogram per second per meter squared, so you already have the meter squared there, so meter squared times meter, you get the meter cube. Okay, so you just convert the kg into kilomole by dividing with the molar mass. So this is your small kya. Then from HL you can get the small kxa. Then this L here is you convert the GX into the molar flow rate, like what we did in the gas flow rate. So you divide the kilogram per second of water into kilomole per second of water by dividing with the molar mass of water. So these are your small kya and small kxa. So when you got these values, you can plug into this equation here. M is the gradient of the equilibrium relation. So previously, earlier in the question, it's given that for the system, y equals to 1.20 times x, so m is 1.20. So then you can calculate 1 over kya, capital Kya equals to 1 over small kya. So small kya is this, 0.0584 plus m, so m is 1.2, divide by small kxa, so small kxa is this value. So then you just plug in the numbers and you get that kya, the big kya is equal to 0.0522. The unit is the same. So from the values of all the capital Kya, small kxa that we have already calculated in example 1a, we can use that to calculate the resistance of gas film and of the liquid film. But since the question asks what is the percent resistance of the gas film, then we want to have a look at the gas film. So this is 1 over Kya equals to 1 over small kya plus m over small kxa. So these are the values just now. So then you can calculate the percent resistance in the gas film. Okay, so this here represent the percent resistance of the gas film, and that is 17.12. This part, okay, this part here. So 17.12 divided by the total resistance based on the gas driving force, this 19.168. So 17.12 divided by 19.168 times with 100%, you get 89.3% of the resistance is from the gas phase, from the gas field. Okay. Now we move on to example 2. For an absorption of CO2 from air by water in a dilute solution in a PET tower with 1.5 inch metal Paul rings at 303 Kelvin or 30 degrees Celsius and 101.32 kilopascal pressure with the given flow rates of Gx and Gy in terms of mass flow rate per area. So predict Hg, Hl and Hol and estimate the percent resistance in the gas film and compare the percent resistance in the gas film for CO2 air water to that of NH3 air water in example 1. Okay, so in example 2, the system is CO2 air water. Example 1 previously ammonia air water. So we want to compare. So the data are given here. And as I said, since this is an exercise, you are given all the data. If not, then you have to find the data on your own. Okay, so you're given all of the data here. Okay, start with example 2a to calculate the Hg, Hl and Hol. So we start with Hg first. So for Hg, the correlation is this from table 10.61 and for 1.5 inch metal Paul ring, the packing factor is 1.34. So you put Fp is 1.34. So NSC, the Schmidt number you calculate based on the data given. So 0.958 here, and Gx is the mass flow rate per unit area, kilogram per second per meter squared given, and Gy, the mass flow rate per second per unit area of the gas. So you put, and then you get the Hg. Simple, because you're just plugging in numbers. Okay, so for HL also, so use the same Fp. And now you need to use the Schmidt number for CO2 in water. So you just plug in the necessary values. And then you use that to calculate the HL. And you get HL equals to 0.2306 meters. Now to calculate HOL, so the relationship that we have derived in the previous lectures on absorption is such that HOL equals to HL plus Hg times L over mv. Okay, so here we need to be careful with the units again. So HL and Hg, they are just height. They have the unit of height, so we can just take it in the unit of meters. But for the L, M, and V, so M here, okay, the relationship given in this case is in terms of partial pressure in relation with the liquid phase composition of the solute of the industry, CO2, CO2 in this case. Okay, so this is the relationship. So you need to convert this relationship into Y in terms of X instead of PA, partial pressure in terms of X. So yeah, you know, PA is equals to YA times P. So YA is PA over total pressure, and the total pressure here is 1 atm. And yeah, you can just, thus YA equals to 1.86 times 10 to the power of 3 XA. Yeah, so M is equal to 1.86 times 10 to the power of 3, and you can take this to be the value of M inside here. But this is a relationship of mole fraction, okay, mole fraction of A or solute in the gas phase to the mole fraction of A or solute in the liquid phase. So when you involve mole fraction, then the L and V here is also in terms of molar flow rate. So you need to convert the molar the flow rates, the mass flow rates of the liquid phase water. So you divide by 18 the molar mass of water, and for the gas phase, to get the V in terms of molar flow rate, then divide it by the molar mass of air, 29 approximately. So you get then you get HOL, this value. So HOL is 0.2322 meter. And this is another relationship to represent the total resistance based on the liquid driving force, HOL, equals to HL. So HL here represents the resistance of liquid film, and this right side term here, Hg times L over mv, is the resistance of the gas film. So if you want to calculate the resistance of the gas film, you take this value. So this value is this 0.001575 divided by the total value. Okay, this total value is 0.2322, then multiply with 100%. So you get 0.68% as the percentage resistance in the gas film. So for question 2C, in the example 2, you are asked to compare the percent resistance in the gas film for the system with the ones that in the previous example. So in this case, the percent resistance in the gas film is 0.68%. This shows that for a very insoluble gas, even though Hg is similar to the in value to HL, the large value of the M, the gradient of the equilibrium data, causes the gas phase resistance to be very small. Hence, the HOL is approximately equal to HL. Okay. And for soluble gases like ammonia, where M equals to 1.2 at 303 Kelvin, compared to for CO2, the M is 1.86 times 10 to the power of 3. The percent resistance in the gas film is 89.3%. So this is just to tell you how the solubility of the gases in the solvent affect the resistance in the gas or in the liquid film. So you can see that the Schmidt number have only very small effect on the results. So it really depends on the equilibrium data. Okay, the vapor liquid equilibrium, the gas solubility in the liquid and the gas phases. Okay, that's all for part 1.